Greetings, my name is Professor Duke Orata. We are continuing with our lectures, and this time we want to look at metastable flow of vapors. We remember we have looked at various aspects when talking of steady state flows. We've looked at various aspects, and so I keep encouraging you to follow our lectures systematically so that we are all together. So let's look at metastable flow of vapors. Metastable flow of vapors. Now, before we leave these aspects of flows in nozzles, we need to look at metastable flow of vapors. And remember, we talked about isentropic expansion of vapors. And ideally, if you consider isentropic expansion of the vapor into the wet region, then the kind of temperature entropy profile which you'll expect will be the one which we are showing here now. So if you consider isentropic expansion of superheated vapor into the wet region, the temperature entropy profile will be what we are showing here now. So if you take the temperature and you look at the entropy, and the kind of profile when you have this isentropic expansion of this superheated vapor into the wet region, remember we talked about this in our earlier lectures. If you look at the profile in the wet region, if you look at our earlier lectures, you're going to see the various aspects of wet region in terms of the dryness fractions and so forth. So if we have the profile, so let's consider a case where we have constant pressure line 1, we have state point 2, state point 1, we have constant pressure line 3. Let's call that state point 1, 2, we have 3. So if you look at those pressure lines, these are constant pressure lines, and so where we have the interface, the wet region, we are expecting, based on elements of phase equilibria, that there should be condensation. There should be condensation. In other words, when we reach the state point 2 here, we expect some condensation to occur. In other words, the kinetic energy of these particular molecules is small, or the velocity of these molecules is considerably low, such that they cannot overcome the attractive forces between these molecules. So we expect that these molecules will actually coalesce into a liquid or into a condensate. So what are we saying? So considering expansion along the constant pressure line at state point 2 in the temperature entropy diagram, we expect condensation to take place. And like we have said, it's because the kinetic energies of these molecules are significantly reduced, such that we expect that they will not resist, they will not overcome the attractive forces between these molecules, so that this these molecules actually coalesce and form a condensate, or they will condense. So what are we saying here? So we are saying that the kinetic energy is significantly small. So cannot overcome the attractive forces. So we expect condensation. But this does not occur. This does not occur. Ideally, that's what should occur. Based on phase equilibrium, that's what should occur. But that does not occur. Why doesn't it occur? Remember, the flow velocity in the nozzle is very high. Is very high, such that the expansion of the superheated vapor will basically be in the dry state. It will be expanding in the dry state. There will be no elements of liquid in it, because the flow velocity is very fast. That's very important for us to note. So it's very, very important for us to note. Though ideally, so what we are saying, though ideally we expect condensation, but there's a caveat: the flow velocity is very high in the nozzle, so that basically we'll have the superheated vapor expanding in the dry state. So the flow velocity in the nozzle very high, therefore the superheated vapor will expand in a dry state. Very important to note that. Now, ideally, we are saying that as we have the expansion, for example, along a constant pressure line P3, then we might not have the state point correspond to 3. We might have the state point slightly at a lower temperature. If we are saying, so the TS profile, the temperature entropy profile, the temperature entropy profile can change significantly, where the state point, the final state point on expansion along constant pressure line will be 3 prime. 3 prime. Now, let's just draw that so that you know what we're talking about. So you remember in our diagram, the ideal one, remember where we have put the state point 3, but we are saying that in real practice, in real situations, you will find that that expansion, temperature entropy again, that expansion as the pressure line 3, you will find that it might actually, the state point will correspond to 3 prime here. Remember, that's our state point 2, 1. Remember, this is our state point 1. Now we are saying that in reality, you will find that that point 3, which we said was here, in the actual reality, it will probably be at 3 prime. That's the state point. Actual state point on expansion. on function along the constant pressure line, 3 is 3 prime. So you will actually find that you will not get it at 3, you will get it at 3 prime. In reality, you expect it, you would have expected it ideally to be at 3. But you are saying that the flow velocity is so high in the nozzle, such that even though to attain the equilibrium, liquid vapor equilibrium is also fast, but the flow velocity is very fast, such that it's kind of delayed. Attainment of proper equilibrium between liquid and vapor is kind of delayed because the flow velocity in the nozzle is very fast, very high, very, very high. So we get that state point. So what are we saying? So the point between 2 and 3 prime. So the point between 2 and 3 prime, it's important to note that. So the states between 2 and 3 prime can be considered as metastable states. And actually they represent supersaturated or supercooled vapor. So the state between 2 and 3 are metastable, and represent supercooled or supersaturated vapor. And so if you look at this temperature, it's lower than what is expected as the saturation pressure, at the saturation pressure. So that temperature is slightly lower. As you can see, it's much lower than what we expect. It's much lower than what we expect. And that's where the concept of supercooled originates from. And these states are metastable. What do we mean by metastability? When you're talking about metastable states, that means that these states, a small disturbance, for example, can lead to condensation. A small disturbance can lead to condensation. Even just introduction of, for example, a measuring instrument in that particular system will disturb the system, can change the state of the system. They are not totally unstable. That's why we call them metastable. A case of total instability will be expected where infinitesimal modification of some variable or some condition in that system will lead to a drastic change in the profile in that system. That's why, if you remember from our lectures in thermodynamics, we talked of, for example, when we talked of thermodynamic reversibility, we said that thermodynamic reversibility is described as a case where infinitesimal modification of a variable reverses the direction of a process. So when you're talking of unstable state, we expect that some infinitesimal modification of some property of that system will lead to a very big change. For example, can lead to condensation at that point. But that's not the case. So in the case, that's not like in the metastable state. So metastable state is not unstable and is not stable. So metastable state is lying somewhere, and it's like in a matrix. It's a matrix between, we have stable, metastable, and unstable. So metastable is lying in between these two domains, stable and unstable. It is not unstable and it's not stable. It's very, very important to get that particular point. Now, what does it mean to us? So it simply means to us that, what it simply means is that if you go to your steam tables, for example, you can look at our lectures on steam tables. We have discussed extensively the concepts of the properties in steam tables and why they are as they are. So I encourage you to go through our lectures where we have dealt with steam tables and just have an idea of what we are talking about. So when you're talking about the steam tables, So we are thinking of, we have the superheated values, vapor values. In our steam table, let's say we have a steam table. Let's say we have our steam tables. And we say that we have our superheated vapor properties. And we have the supersaturated vapor. Now, properties. Unfortunately, the superheated vapor properties do not move systematically into the supersaturated vapor properties. So what does that mean? It means that we have to make an assumption that when you are dealing with computing values involving supersaturated vapor, then you can assume that the properties are closely related to that of superheated vapor. And so, in terms of using the polytropic equation, we can use the polytropic equation for the superheated vapor on supersaturated vapor. Very important for us to note. The values of superheated vapor do not move into the values of supersaturated vapor. So we can just extrapolate when you are working in a supersaturated vapor by assuming that the properties of that superheated vapor, even if it was just a little superheated, and then it collapses into the wet region, we can assume that the properties of the supersaturated vapor can be accounted for by the polytropic equation for the superheated vapor. Very important for us to note. Given that the properties of superheated vapor don't extend into the supersaturated vapor region, we can assume that the supersaturated vapor obeys the polytropic equation. So we can use the polytropic equation for the superheated vapor as relatively accurately representing the properties of the supersaturated vapor. And the polytropic equation, if you recall from our lectures, again, if you look at our lectures on polytropic equation, we have the equation PV 1.3 is a constant, or P over T 1.3 over 0.3 is a constant. And remember, 1.3 is N, which is the isentropic expansion index. So, like you're saying, you can use that polytropic equation for the superheated vapor to account for the properties of the supersaturated vapor. For example, to compute the final state, you can use that to compute the final state and even the drop, or even the drop isentropic drop in enthalpy. Isentropic drop in enthalpy. Remember, we talked about that from the beginning when you're talking, for example, isentropic change in entropy. Remember, just recall, we said in passing, H we said was U plus PV. If you remember, we know what H is and what U is. And so we are simply saying that H is equals to U plus PV. So we are simply saying that DH is equals to DU plus P dV plus V dP. If you remember the early lectures in steady flow and jet propulsion, I think is the first one. And we said that DU we know is dq plus dw. And what is dq from Clausius inequality? We say that dq is TdS. Because remember, from Clausius inequality, dq over t is greater or equal to ds. Or can say ds greater or equal to dq over t. So dq can be equal to TdS. And so if we put that there, so we are saying dH is equals to dq. Remember, we have dq plus dw plus pdv plus vdp. And what is dw? That is minus pdv. So we have dH is equals to dq minus pdv plus pdv plus vdp. And this is TdS. dq we have said is TdS. So we have TdS minus, of course, those two cancel, plus vdp. So under constant entropy, ds will be equal to 0. So dH is equals to vdp. So we are talking of computing even isentropic drop in enthalpy. Remember, isentropic drop in enthalpy at that particular point, isentropic means constant enthalpy. So we have dH is equals to vdp, and we are able, using polytropic equation, to compute that. And our assumption there is that the supersaturated vapor obeys the polytropic equation for the superheated vapor. So let's stop at this particular point. We are still continuing with our lectures on steady state flow, on steady flow and jet propulsion.